Let us now see how we can make a simple asynchronous counter by making use of the already available T flip-flop. So therefore, let us have a new project. So we'll name it as a ripple counter. And we'll say okay. So ripple counter is nothing but an asynchronous counter, and we'll create a new file which is a Verilog type, and we'll call it as ripple counter as well. Now let us add the existing T flip-flop file to the project. This is the T flip-flop file which we have already created. So this is what the T flip-flop looks like. This is a positive edge triggered T flip-flop. So if you recall our theory discussions, you can use positive edge triggered T flip-flops in an asynchronous manner by feeding the Q bar of one flip-flop as clock for the next flip-flop, and the outputs as always would be taken from Q. So therefore, let us define the module ripple counter. So over here, the output obviously will be something called as count, and the input will be clock. Let's keep these two simple inputs for the time being. And now let us declare output. Let's define a 2-bit counter. Let's define a 3-bit counter. So that means Q2, Q1, Q0. So we will say 2:0 count and input clock. Now let us see what the T flip-flop needs. It needs the T input, it needs clock, there are Q and Q bar also. So therefore, the internal connections we can define. Let's call them as some wire. Let me call the outputs of the flip-flop the outputs of the 0th and the first flip-flop as a 2-bit variable Q1 and Q0. Similarly, we can call for Q bar also, which are the outputs of the 0th and the 1th flip-flop. So therefore, now let us start instantiating the T flip-flop. So we will call the first T flip-flop, we'll name it as T0. So we'll say T flip-flop. This was a capital, I guess. Yeah. The instance name is T0. Now let us write the order. So this is the LSB flip-flop. You need Q, Q bar, T and clock. So since we want that the Q of this should correspond to the 0th bit of the count variable, we need not use this Q variable. In fact, we can do away with it altogether. We can just have Q bar. We will say count of 0, comma, Q bar of 0 followed by T and clock. Now T always has to be 1 and the main clock will come here. This is instantiating or invoking the LSB flip-flop. Then I will call the next one, the 1th flip-flop. Let's call it as T1. So over here, the Q will be count of 1. We will call this as Q bar of 1, the T input will be 1. Now here the clock input will be Q bar of 0. That is what an asynchronous counter is. So therefore, let us make this Q bar also as a 3-bit variable, just for the sake of completion. And finally, the third MSB flip-flop, we'll call it as T2. This bit will be count of 2, then Q bar of 2. The T will always be 1. Now here the clock will be Q bar of 1. This is the invoking of the MSB flip-flop. So this is what it looks like. So there are 3 flip-flops to be used for this 3-bit counter, and we have invoked them in a structural manner. So therefore we will just stop here and say end module and save this. Let's execute all of them. So both are successful. Let us now see what happens, whether it executes. So in work, I will click on ripple counter and I'll say OK. So I'll go to the wave. I will add clock to the wave and count also to the wave. Let us see what happens. So I'll give a clock over here with period 100. Let us see if it counts. So initially it was 111 for some reason, and then it became 000. Then 001, 010, 011, 100, 101, 110, 111, and then again back to 0. So you can see each of the waveforms of count 2, count 1, and count 0, which is nothing but Q2, Q1, and Q0 of the flip-flops. And they are changing in a divide by 2 fashion, as we have discussed in the class, and they are changing at every positive edge, as we expect. So this is how we can define a simple ripple counter or asynchronous counter in a structural manner using T flip-flops. Let us now do the same thing, that is to design an up counter, 3-bit up counter, but using the synchronous technique. So therefore, let me close this project. So I'll call this as synchronous counter. So I'll create a new file. I'll call it as synchronous counter. I'll say OK. I'll also add the existing T flip-flop file, which is there, because I'm going to do this also in a structural manner. So let me close the ripple counter file, and I'll open the synchronous counter file and describe the module. So I'll say module synchronous counter, and the output will be count, input will be clock. Now I've already done the design steps wherein we need to construct the state table having the present state and the next state, and solve using the excitation table for whatever will be the values of T. So essentially here we will again need 3 T flip-flops, and we have to essentially calculate what will be the T input. Here, of course, the clocks for all the flip-flops will be the same. Now, what will happen? Let's declare them. Let's say output 2:0 count and input clock. Now let me declare an internal connection called T. I'll say 2:0 T, which will indicate the inputs, the T inputs for each of the flip-flops. So I have already calculated what will be the expressions for T2, T1, T0. So I can simply use data flow statements, that is assign T of 0, which is the LSB, that is equal to Q2 bar, or rather I should say count of 2 and count of 1 this thing odd with the not of count 1 ANDed with count of 0 this odd with count of 2 bar ampersand count of 0, which is an AND operation. That's it for T0. Next, for T1, that will be a little bit simpler, which is not of count of 0 odd with count of 1. You can verify these expressions yourself by solving the state table. Finally, for the MSB flip-flop, T2 will be equal to count 1 odd with count of 2 ampersand count of 0. So I'll say these expressions are obtained by constructing the state table of the counter and using the excitation table of the flip-flops. So we have defined this thing. Now let us invoke the T flip-flop that we already have. So I'll say T flip-flop, I'll call it as T0, the LSB flip-flop. What are the things we need? We need Q, Q bar, T and clock. So let us define wire 2:0 Q bar. So here the Q will be count of 0. The Q bar will be Q bar of 0. So it does not matter whether the name Q bar here and the name Q bar inside this T flip-flop description is the same. It does not matter. And then the input will be T, which is over here already defined, T0 and clock. Next, T flip-flop, T1, count of 1, Q bar of 1, T of 1 and clock. Here, as you can see, all flip-flops get the same clock. T2, count 2, Q bar of 2, T of 2 and clock. That's it. Finally, we'll say end module. So let us run them. Let's see if they accept. So as you can see, both executions are successful. So let us therefore start the simulation. So here I'll say synchronous counter. So I'll say add wave clock count, also add wave. Oops. Clock of 100. Let's see what happens. So here you can see there's a bit of a problem. Here the state is going from 0 1 0, then 1 0 1, then 0 0 0, 0 1 0, 1 0 1, like that. So that means probably we have done some mistake in the code. Let us end the simulation and see again. Let us see whether something else was the mistake. Q2 bar, Q1, Q1 bar, Q0, Q2 bar, Q0, Q0 bar, odd with Q1, Q1 odd with Q2 and Q0. Looks to be fairly okay. That means probably the analysis which I have done is incorrect in some way. So therefore I leave it to you to find out what the mistake is in my analysis and implement this code correctly. So here we have seen how to run this, how to use the existing T flip-flop in a synchronous manner, again using structural description where we are using the already available elements. Yeah, so I found out the mistake. So essentially what will happen is that T of 0 would become totally 1, and T1 would be count of 0. That's it. I had made a mistake in writing the state table, and T2 would be count 1 ANDed with count 0. Yes, that's it. So now let us run it again. Let's run it again and then see what is the simulated waveform. So over here, I'll place clock to wave. I'll give it a clock of 100 and let's see if it works. Voila, it works. So I found out the mistake and I rectified it. Thank you. Let us now see one of the simplest ways in which to describe a counter, that is in the behavioral way, where we don't have to worry about whether it is synchronous or asynchronous. So therefore, let us make a new project. Let me just simply call it counter. I'll create a new file, also named as counter, and I'll close these files. I'll simply now define the module. There will be just one output count and one input clock. Let's say I'll define it again as a simple, let's say I'll now define it as a 4-bit counter. So since I'm going to be using behavioral constructs, I will put it as a reg type of 4 bits called counter. and input clock. Now let me write an initial block. I'll say count in a blocking statement equals 0. So I'm going to forcefully initialize the counter to 0. And then I will say always @ posage clock, and over here I will say count equals count plus 1 and end, then end module. That's the simplest counter you can ever have. So therefore, let's see if it works out. The compilation was successful. We'll start the simulation. Add the clock to the wave and the count also to the wave. I'll assign a clock of period 100. Let's see if it works. Yes, 0001, 10, 0011, 0010, 0110, 0111, all the way till 15, and then again back to 0. This is one of the simplest ways through which you can describe a counter in behavioral fashion.